Bismillah ar-Rahman ar-Rahim. My dear students, the title of my lecture today is Intensity Modulation Direct Reaction System. It is one of the lectures given for our course Advanced Optical Communication System. The lecture consists of two parts. The first part deals with the main concept of intensity modulation direct detection, IM/DD system. The second part concerns with the mathematics behind or mathematical framework. It is much better to say that for detection process in the receiver side. Recall that we usually in communication systems we have two detection processes. Direct detection and coherent or sometimes called synchronous detection. Direct detection likes envelope detector used to detect AM signal, double sideband with carrier. While synchronous or coherent detection, we must use a local laser in the receiver side, operates synchronously with that used in the transmitter side. This has been used for single sideband AM signal, for double sideband surprise carrier AM signal. In optical communications, the main concepts are applied. In direct detection, we use a photodiode at the receiver side to convert the received optical signal into electric one for further demodulation. This will be used here. So our title of this lecture, Intensity Modulation like AM, Direct Detection System, like AM in conventional communication system. The other one, which is more expensive, is the coherent or synchronous detection. In optical communication, the receiver must use a local laser, operate synchronously with that used in the transmitter. Coherent detection, which is the subject of next lecture, is more expensive, but it gives more performance compared with direct detection. The intensity modulation direct detection optical communication system may be used for analog modulation. The signal is analog and the intensity of the laser is varied linearly with the information and message, the electrical message. Or digitally, where the optical source, laser or light emitting diode one, is switched between on and off state. In on state, there is optical pulse transmitted in the fiber, and in zero state, the optical source emits zero power or low level of power compared with state 1. This is a simple block diagram showing the main concept of components and component use in intensity modulation direct detection. We have information input, message, and we have the drive. This is electrical to optical interface. The data is embedded in the intensity of the optical source. It's transmitted through the link. In the receiver side, we have a photodiode to convert the signal from optical domain to time domain and then demodulated in the electrical domain. In analog intensity modulation, we must use a linear part of the current power characteristic of the optical devices. We usually use light emitting diode for low bit rate transmission, for low distance transmission, and laser source for high bit transmission and long distance transmission. Please look. The power current characteristic of the light emitting diode is almost linear without a threshold. If we use laser source, we have a threshold. After the threshold, the light varies quickly with input current. Below threshold, the laser is almost off. If we use the laser for analog modulation, we must choose a linear part of the power current characteristic above a threshold. This is very important point. Remember also that light emitting diode have continuous spectrum. It is not ideal optical source. The laser have discrete spectral components of when a single mode laser is used. Theoretically, we have only one emitting frequency. The spectrum is delta function, but due to spontaneous emission, the spectrum becomes wide, and this is called laser line width. Laser line width is 0 if the laser is ideal single mode. It is more than 0 due to spontaneous emission associated with the transmitted or emitted single mode في هذه الحالة. What our challenge or limitation from the source, from the optical source side of view? Power important, especially for analog modulation. Response, is the optical device responds quickly to the driving message or not? Linearity between the power, emitted power, and current. This is important for analog modulation. Spectral width. If we use a semiconductor laser and has certain spectral width, the laser will not respond as ideal source. Thermal. Laser or light emitting diode operation, the temperature increase, due power consumption, we have current, we have voltage, so the temperature of the optical device must be under control. Non-zero excitation ratio. This is the ratio between the laser output power when it is operated in the on state divided by the output power when it operates in the off state. This is for digital system. Theoretically, it should be very large, infinity, when the laser source emits zero power at the off state. In analog transmission, maybe, or it is important to use This is more correct. Linearization networks to compensate any nonlinear variation between current and emitted power. This is useful to reduce distortion of the output modulated signal of the transmitter. Linearization, different techniques we can use. Maybe use a transmitter side, at the receiver side, or both. At the receiver side, it is important to use the linearization here, because the signal, the optical source, is under control. The optical power after modulation, or the power of the optical signal, modulated optical signal, is high, clean, there is no noise, while at the receiver side, the signal optical received is low, embedded with noise, and the linear equalization should be used after the photodiode. Linear equalization here is done in the electrical domain, either at the drive circuit of the laser or at the drive circuit, or after the photo detection at the receiver site. We look here, we have linearization network at the input. We have also a linearizing network at the output after the photo current. Sometimes we use part of the power emitted from the laser or from the optical source at the transmitter side to control the optical source. Look here, most of the power is coupled to the fiber. Few power is detected by photodiode, kept under monitoring. Maybe feedback will be used to control the drive circuit, and this is useful, for example, to keep the emitted power from the laser source constant when the temperature varies due operation, for example. This is a more complex concept for controlling where the input signal is phase shifted by 90 degrees for analog modulation. When we use laser in digital modulation, we must keep the laser near threshold, the bias of the laser near threshold at the off state. So the laser is ready to be on when logic 1 is come. If we bias the laser below the threshold, laser 1 comes, the laser must takes time to build the inverse population and then emit the required power at logic 1. So usually digital modulation, intensity modulation, when the laser is driven by the off state, the threshold is not switched to 0, it is switched to near threshold, just above a threshold. This system shows how we control the mean power of the laser using feedback. Look, the laser is driven by two currents. One is the bias, time independent, and the other carries the copy of the modulating signal. It is time dependent. in analog modulation, this is small, and this is the main part of the drive current. Feedback is used in this case through photodiode to control the bias current, and this technique keeps the power emitted from the laser average power constant. Please look at this diagram, which shows the optical receiver circuit, which is simply optical detector, usually pin or avalanche photodiode. Low photocurrent is generated here, embedded with noise. Electrical amplification through many stages. Equalization is used to equalize the shape of the pulses, which is very important in digital modulation, and filtering for low pass implementation. As in analog modulation, the receiver must be used automatic gain control to keep the output of power electrical for the terminal constant, independent if the received optical power is not constant. I mean, when the received optical power varies, the receiver, it tries to give almost constant output electrical power in this case. If we look here, this is avalanche photodiode, where the gain is controlled through the voltage, and we have here what is called peak detector diode, low pass filter, like the envelope detector used in AM modulation. And the feedback will control how high voltage required to bias the avalanche photodiode. The gain of the avalanche photodiode is a function of this bias voltage. The AC couple is used to remove any variation due modulation. Equalization is similar to the equalization used in any conventional communication. And when the signal is passed through any block of the communication system, the block is characterized by impulse response and transfer function. Time domain, it is convolution. Frequency domain, it is multiplication. And the equalizer stage of the receiver side is added to obtain output pulse or signal having certain required characteristics. Old version of optical communication system uses optoelectronic repeaters during the link. When the link is long and the signal attenuated and distorted, we must use a certain point through the link, what is called optoelectronic repeaters. It is simply an optical receiver, then to detect the signal at that point, remove the noise, equalize the shape, synchronization, repairing, then the electrical clean signal will be used to drive an optical transmitter. It is costly unit, but was important in these days because it used optical transmitter and driven by optical receiver. Different parameters causes error in optical receiver in our case. Is the signal to noise ratio low or high? Lowering the signal to noise ratio of the receiver side may cause error in detection process. Intersample interference. The sample under decision may be overlapped with the neighboring samples. Jitter is the clock recovery at the receiver side matches exactly that in the transmitter side or not. Look into this figure, what's called eye diagram. Eye diagrams is simply a geometric local of the various patterns in this case. I mean, there is sample under decision, maybe, for example, say state 1, but 1 before is logic 1, after logic 0, maybe the other cases 0, 0, 1, 0, 0, 1, and the sample is under investigation, subject to various variation of linearizing sets. If we look here, we see this is the eye opening. It is open. This is logic 1. This is logic 0. This is the decision level. Not the eye opening is clear. In the other case, if we look here, we see the eye opening is not open smoothly. The eye opening is reduced. In this case, equalization is almost good. In this case, the equalization is relatively bad. In this figure, shows the modulation format used in our binary modulation. It is either non-return to 0 or return to 0, similar to the two concepts have taken in the communication subject. And return to 0, for example, 50%, it means that during state 1, the laser emits power only 15% of the bit period and then turns off. During logic 0, it is already reduced off in this case. Generation return to 0 pulses is more expensive compared with non-return to 0. And if we look at this figure, we use two Mach-Zehnder modulator, one to generate all the pulses, but the top is not constant. And the other one, Mach-Zehnder modulator, to equalize this amplitude variation and generate optical pulses, digital, with constant amplitude in the logic 1, because in the logic 0 the power is low. In this figure, we calculate the eye closure penalty at the transmission distance. What we mean by eye closure? It is 10 log the eye opening when the transmission distance is 0 back to back, and the eye opening after certain distance. For example, At 5 kilometer, if we will find the eye opening 0.7 and in 0 distance the eye opening 0.9, the power penalty at this distance is 10 log 0.9 over 0.7. 0.9 is the eye opening when the distance is 0. 0.7, for example, is the eye opening after a distance, for example, 400 kilometer. This figure shows clearly that return to 0 can support more distance compared when rotate to 0. If we use, for example, with the penalty, for example, for dB, no rotate to 0, 300 kilometer, and therefore about 50 kilometer rather. This is the first lecture, and the second lecture will deal on the mathematical concepts of optical receiver and different forms of optical intensity modulation formats. Thank you very much for listening, and please come and touch.